students, today we are going to discuss about Thevenin's theorem. Okay. For that, I am taking this circuit. As you can see, you need to find the Thevenin's equivalent network across A, terminal A and terminal B. Okay, so you need to find the Thevenin equivalence network across the terminal A and B. So this is the terminals A and B. You can see. So between A and B, no elements is present. If there is an element, say R, present in between A and B, then firstly what we have to do is, firstly you have to remove this element. After that you have to go to find the Thevenin's equivalent network. So let us first find the Thevenin equivalent voltage, which is denoted by VTH. Let us find VTH first. So VTH is nothing but your open circuited voltage across this terminal. So as you can see, this terminal A and B and the series combination of these elements as well as this series combination of these elements are in parallel. So if I can somehow find the node potential at this point or the node potential at this point, then that voltage would be equal to the VTH. As we know, there is these two nodes. Say I will denote these nodes as C and this node as C as well. Since there are no elements in between, so this node and this node basically represents the same node. Okay. So now let us simulate this circuit in the Multisim software. For this, we have to open the Multisim software. So this is the interface of the Multisim software, as you can see. So there are different families of elements over here. So let us first click on this base source and let us first select the sources. Say for example, I am selecting your voltage source. For that, I'll be selecting this signal voltage sources. Okay, under this you will select DC voltage, click OK. So this is our voltage source. The voltage source has been selected. Nextly, I will select the current source. So let me select the current source. Okay. Let me check the circuit. The circuit, as you can see, we have two resistance values and one inductor. So let me select the elements. So I will go to here, place basics. I will select the resistors. So resistors need to be rotated. So I will rotate the resistors while selecting. To rotate, press Ctrl R. So nextly select the inductor. Press Ctrl R so that we can rotate the element. And what I need is I need a ground. For that, I have to go to sources, power sources, and select the ground. Press OK. So this is our fine. So nextly, what I have to do is we have all the elements in this Multisim software. So now we have to make the connections. So let us make the interconnections between the components. Okay, I'm done with the interconnections. So now I will change the values as required. So I will check the circuit once again. We have 1 ohm and 5 ohm resistor values. So I will change these values. To change these values, just double click on it. So this resistance value is of 1 ohm, is 1 ohm. Next, I will change this resistor value to 5 ohm. This is your 5 ohm. And let's check what is the value of the current source. It is 2 angle 45 degree. So I will change the AC analysis magnitude to 2, and I will change the AC analysis phase to 45 degree. So I want to point out here that for single frequency AC analysis, we only need this two values, that is AC analysis magnitude and the phase analysis magnitude. Okay. Only these two values need to be selected. The rest values will be not be used in case of single frequency AC analysis. So what you can do is you can just place 0 elsewhere. Okay. Since these values are not going to be used, so it doesn't matter actually. So I will be giving the AC analysis magnitude as 2 and phase as 45 and press OK. So nextly I will modify the voltage source. So voltage source is 10 angle 90 degree. So similarly I will change it to 10 and the phase angle as 90, and rest could be zeros, and press OK. So nextly I have to change this L value. As you can see in the numerical, we have L value given in the phasor form or frequency domain form. So I have to find the value of L, that is your inductor value. So for this I will be using the formula. As you know, XL equals to J omega L. So XL is given as J2, so I will write J2 equals to J omega. Omega is nothing but twice pi f. Pi f into L. So I can cancel out 2J from both the sides and find the value of L as L will be equals to 1 by pi into f. Now in the question, as you can see, the value of the frequency f is not given in the numerical. So you are free to select any frequency. So for our example, let's say I will be taking frequency f as 50 Hertz. Okay. So if I select f to be 50 Hertz, then the value of L would come to, so let me bring the calculator. So the value of L is 1 divided by pi into 50. So this would give me 0.0063. So the value of L, I can write it as L equals to 6.3 millihenry. So this is our value of L. So now the value of L should be calculated. So I will change this value to 6.3 milli. For milli, I will write small m. Press OK. So finally, this is our circuit. So in this circuit, I'm going to find the node voltage 3. As you can see over here, we have 3. So 3 is our node or net name, node name or net name. So this particular node is your node 3. So I need to find this node potential. For this, I will go to simulate, analysis and simulations, select the single frequency AC. Now you have to select the frequency. So you have two options. You can either give it manually or click on auto detect. Now while giving the values in the source list, I haven't set the frequency component. So I have to give the frequency manually. Otherwise, if I set the frequency to 50 Hz say over here, then I can select the auto detect option. Now since I haven't given any frequency, so I have to give the frequency manually. So let's say our frequency is 50 Hz. Okay. Next, I will select the output. Now our output will be in the tabular format. Okay. So if I want one of the coulomb to be the frequency, then I have to check this box. And nextly, as you know, the phasors can be represented either in the rectangular format or in the form of polar format. Okay, so we have two options over here. So I will be selecting your polar format, that is magnitude oblique phase. So next I will go to output. As you can see, this pen, the left pen, contains many variables in it. So out of these variables, what I need V3. Okay. So as you can see how these variables are denoted. The first letter is if the first letter is V, it denotes your voltage. Okay. And by 2, 3, 4, it denotes the node name or net name. So in case of multisim, the node is represented or assigned as net. Okay. So V3 means the node voltage at the node 3. So I want this voltage, and this voltage will be equals to our Thevenin voltage. So I will select it and click on add. When I click on add, you can see this V3 will be transferred to the selected list. So this right pan is the list of variables that has been selected for our output. Okay, so I will select this V3 and click on add. So as you can see, when I click add, then V3 is selected. After that, I will click on run. When I run these simulations, as you can see, V3, which is nothing but your VTH, this is the variable, and calculated at frequency 50 Hz, and its value is magnitude wise it is 6.48, and it has a phase angle of 112.4. So that's how we can calculate the value of VTH in this circuit. Okay. So let me show how to calculate the ZTH. So for that, what I will do, I will just copy this figure so that I don't have to make the circuit once again. So for that, I will just left click and drag and press Ctrl C, copy this entire circuit. Then to paste, I will press Ctrl V. So this is our circuit. So as you know, in case of while finding the ZTH, so how ZTH can we find out? By removing all the independent sources. So as you can see in the circuit, we have two independent sources, namely this current source and other is your voltage source. So these sources need to be removed. So how can I remove or turn it off? The voltage source is turned off by pressing a short circuit, and the current source is turned off by open circuiting the current source. Okay, so this will be short circuited since this is a voltage source, and the current source will be open circuit. So let us do the modifications. I will just short the voltage source and open the current source. So this is our final circuitry. So for ZTH, we will be looking from this angle, that is from right to the left. Okay, so this would be equals to 5 parallel to 1 plus J2. Okay, so this is how the ZTH can be find out. But by using Multisim, how you can find out is you just go to this tab below this lab instrument. As you can see, click on it, select the impedance meter, just connect it across this terminal. So one thing you have to notice that to find the value of ZTH, you have to remove this ground, and also you have to set the frequency. So double click on it. If I double click on it, you can see there is start value and a stop value. So I only want the value of Z for one definite frequency, that is your 50. So I will change this start and stop value to 50. Okay. So if I click on run, you can see the previous result of VTH has been displayed. So firstly, I have to stop this single frequency AC analysis. For that, just what you can do is you can just click on simulate analysis and say, for example, press on the first link and save. Click on save, just click on save. And now if you run the simulations, you can see the result over here. So R is 1.24 and X value is 1.23. So from this, you can write ZTH as, so ZTH would be equals to 1.24 plus J 1. Is also approximately equals to 1.24. 1. So this is our ZTH value. So what does this plus indicates? Register value of 1.24 in series with J 1.24 inductor. So this part is nothing but your inductive reactance. I have a negative sign over here, then it represents your capacitive reactance. Since that's how we can find the ZTH and VTH for a Thevenin equivalence. That's all for today.